point of view, or in the so-called strong gravity regime. Now I realize a lot of particle theorists, and most of you are particle theorists, so there's nothing to do with strong coupling. By strong gravity, I only mean that the curvature, 3 and 4 curvatures are high. And one way of seeing this, for example, we know that in a homogeneous and isotropic background, the 3 and 4 curvatures are measured by the Hubble parameter, or its square. And again, just for bookkeeping, I will keep everything in 10 minutes. So you can measure the curvature and relevant dimensionalities, which would tell you how strong the gravity regime is in terms of the Hubble parameter. And we know that for most parts of cosmic history, it's fairly big. So we are neither in the perturbative regime of Newtonian gravity, if you want to describe the universe, nor in the perturbative regime of Minkowski space. So the question really is, why don't we need all the time numerical relativity? Why do we get by with perturbing equations and a simple background? Well, this is because the universe is simple. So the best answer to it is we are really lucky. We get really far, and the universe is simple in two senses. In the one sense is that our background geometry has a single, simple, homogeneous dynamical component. So we know that it could be, within the context of curved spacetime, arbitrarily complicated. So we could have a symmetric metric tensor in 3+1 dimensional spacetime, which has 10 independent components, which are both a function of space and time. But instead, what we get from nature is that for the past 14 billion years, our spacetime geometry can be described in a very simple way, where all what we need is to track the evolution of a homogeneous quantity, the scale factor, throughout cosmic time. And how we track it, this is the second and again independent simplification. What we get from nature is the dynamics. Again, we know that, and as far as we know, for most of the energy scales that we can access observationally, and which are relevant for cosmology, the equations that govern the dynamics are really complicated. So these are the 10 independent components of the Einstein equation, which is a set of coupled nonlinear partial differential equations. And we know that we have to supplement it by the evolution equations for the stress energy. The sources are geometry. So this is just the usual notation for the Einstein tensor, and this is just the usual notation for the stress energy tensor. We won't need it. But what we have is instead, because of the symmetry of the background, as we know from observations, as we substitute this very simple line element, very simple geometry, spherical, symmetric, homogeneous, and spatially flat. So just again for bookkeeping, this is the FRW geometry. If we substitute this into the Einstein equations, then instead of having to track the 10 plus nonlinear coupled PDEs, partial differential equations, but we end up with our two very simple equations. One is, many of you know, for example, the Friedmann constraint. This is just the energy conservation equation of general relativity for a simple Friedmann-Robertson-Volta background. And we can track, so the second order equation for a scale factor of first order in the Hubble parameter H. Rho is the energy density of the dominant dominant stress energy component, drives the evolution. It's simple given by so-called perfect fluid approximation, where any form of energy density due to symmetry of the background takes a paratopic perfect fluid form that can be simply characterized by the ratio of pressure and energy density. Again, for bookkeeping, we will call this ratio here epsilon. So this is simple, right? But this works. And why it works is it could be different. It could be that this solution, this line element is a simple solution, but this solution is unstable. And why is it stable? Well, we know it from observations it remains stable. That's one of the questions. So that's the reason why we don't need numerical relativity for to describe cosmic history, because we got a break from nature. Obviously, what we do normally, and many of you work on it, we don't stop with the homogeneous background evolution. What we are used to is we take this very simple set of ODEs, ordinary differential equation, and then on this background, where the essential nonlinearity of GR is encoded, what we do is we do perturbation theory. both cosmological perturbation theory and then more interestingly, quantum field theory inspired effective field theory. Many of you are experts here, more likely more than I am on this issue. And also one lets the stress energy be inspired by Marlow brilliant. But that leaves us still a lot of questions open. So what I want to do in the next 40-45 minutes is to show you how this method of homogeneous background evolution supplemented by the tools of cosmological perturbation theory, effective field theory, quantum field theory, ideas from string theory can be complemented by numerical relativity to answer questions that cannot be answered by this even though powerful but nevertheless limited method. So I'm not selling this, what I'm doing as a replacement for many have done, or many of you are doing. I believe that the best use of numerical relativity in cosmology is to use it as a complementary tool to start a discussion between what was done and how good are the particle approaches and how to further develop them. For example, how good are, so what are the questions that are obviously open and cannot be answered by perturbation theory? The simplest questions are in the early universe when we cannot assume the metric to be that simple, either because we don't have observational access to it, or because the question, and this is what I want to discuss, what we have is, how do we get to the simple line element? And at least classically, so of course, obviously, we can always say, oh, we could just get that from quantum gravity. This is just, there was a Big Bang. Once we find the quantum description of the Big Bang, that will give us exactly this space. That's a valid approach, but for the time being, and short of having such an approach, one could also ask the question, can we find leading order classical mechanisms that start with fairly general geometry, fairly generically, and lead us at energy scales where Einstein gravity already describes very well the leading order evolution dynamics to a line element as we observe. So that will be the central example of the talk, how do we do this? And so I will use this example for both to show you, short of movies, how powerful this tool is, but also more importantly, to show you the concepts. Why? So obviously I don't want to give you a full introduction to numerical relativity here, but what I want to show you why it's different. Why it's different both from pencil and paper calculations and both from other type of simulations that people here do, people at the CCA do, or elsewhere in cosmology. So it's different in both ways, from the approach, from a theoretical approach, and also from the computational approach. But there are other examples too. So that's not the only thing I'm working on. Obviously, you might ask the question, what if I modify GR? How do we explore the nonlinear regime of modified gravity theories within the regime of validity? How do we know that our EFT, effective field theory approximation, is everything, is, for example, a stable solution? Those are questions that are also very interesting, and they are at the forefront of both gravitational wave research, and I believe it should get to a forefront of cosmology research, because things are not yet that well explored mathematically. We will get to that later for those theories. And obviously, there is a third question. What one can ask is, when we don't have a canonical scalar, but something more complicated that has an inherent nonlinear structure, again, how good are our EFT solutions or the leading order background solutions around which we perturb? So those are all questions that one hopes to be able to answer with numerical relativity. But I want to today, yes?
What happened in the special case where the pressure is zero, where it's just dust?
That's dust, yes.
So is that then that you have analytic solution to this equation?
That's just matter domination, yes. There's just simple matter domination that comes after radiation domination. You do. This is here energy density, so this is always an epsilon would be just here, you see 3 halves and simple minus h dot over a squared is 3 halves. So this is just simple matter domination after radiation domination. Yeah, good. So now, just to be on the same page, what I want to go through now in order to be able to do the non-perturbative blackboard numerical part of the story is, what I'd like to show you now is, what is the theory or what is the idea that we have, that many of you are familiar with it, a lot of experts here, of how to get to, from a more general initial conditions, to our simple universe, and what questions are open. And please ask questions in the meantime. And why those questions can be well addressed numerical relativity. So what our real question is when we ask, how do we get to the simple universe described by the simple geometry and simple dynamics? And what we want to know is really the following. If we look at the early universe, well before nucleosynthesis, but at a time where we assume that the temperatures, the energy densities, and everything else is already low enough that a classical GR approximation is valid, then the question of how do we get to our simple universe can be, or is typically written in the following way. I will call the fourth radius finding with smoothing mechanisms. And smoothing, by smoothing, I mean having a dynamical mechanism that leads us to a flat FRW space-time. And typically we start, so this is the really powerful picture that since the 80s, I would say gave the foundation for all development in cosmology. We start with some patch, some physical patch, which has a radius or not. And at this time, we consider the patch that's exactly the same size as our Hubble radius. And the Hubble radius is an important quantity and we'll track it because as one can see already from these equations, where one compares geometry with the dynamics, where we can mostly see, or most impressive we'll see, that we live in a relativistic and not Newtonian universes to really deal with two dynamical scales all the time, even on this simple background. The one scale that was already there in Newtonian physics is simply the scale of any arbitrary patch. And that scale was with the scale factor. However, there was a second scale, and very roughly speaking, for the purposes of the Brown Bag lunch, we could think of the Hubble radius as a basic radius of interactions or causality, again, in the pedestrian language. And now you ask the question, what do we need? Well, we know it again from observations. And I'm sorry for repeating something that we all know, but give me one more minute, then it can become interesting. We need at the end of the day, at the end of whatever smoothing mechanism is, a physical patch that's exponentially bigger, let's say in radius e to the 6 or 60 e-folds bigger than the Hubble patch. And there are naturally two solutions to this in a classical way. One of them you all know, the other one less. The one is, in an expanding universe, keeping in mind that the Hubble radius always have to shrink, as you can see it from the Friedman equation. The one thing what one can do is a so-called de Sitter type expansion. So one keeps the Hubble radius nearly constant. By the end of the smoothing phase, Hubble radius hasn't changed much. And what remains as is one grows with patch size. And this is what we call accelerated expansion. You can also see why it works. And in order for it to work, what we do is how we figure out what we have to do for it is the following. And this is where it comes in. As a pencil and paper, we cannot do everything. But we assume about the original patches. It is not exactly FRW. I say it's, and this is again, only the pedestrian way. What do I mean by it's almost FRW? But what I mean is that we take really simple deviations from a simple flat FRW line element, deviations that on the one hand are still solutions to the Einstein equations that give us enough hint about what we have to do if we are not exactly FRW to get there, at the same time get there on super Hubble scales. And there are also patches that, and this is really was the idea already in the 80s, and I know that Matt lately has done work on it in the context of inflation. These are patches that we assume are reasonable to assume. Even if they are right, it's reasonable to assume that there can be such patches in the universe. And if there are such patches in the universe, short of doing simulations, we can show by pencil and paper that we can get to a large homogeneous smooth and flat patch on super Hubble scales. And almost FRW would mean it is we add simple anisotropy and simple spatial curvature to the Friedmann equation that normally could be dominated by matter, radiation, spatial curvature that you all know, and a very simple kind of anisotropy. But I only introduce anisotropy in the way that instead of this simple line element, this is the simplest for the expert Kasner type of anisotropy, that on the diagonal, so instead of having a universe that in each spatial direction evolves, expands in the same way at the same rate, I introduce a universe that in each spatial direction at every point, it can expand in two ways and contract in other, and which direction contract and which directions expand switches with time. So this is what I call almost FRW. This is a typical assumption. And we can read off from this equation both why we have a problem and how we can solve the problem within an expanding phase.
I think I'm confused about
Yes.
that last. Maybe I didn't hear it completely well, but the notation makes it look like it's spherically symmetric,
It's almost spherically symmetric.
but
Um,
you're just what this is
So-
somehow the average scale.
Exactly,
and-
very good. So typically we introduce a Kasner type metric, which means that if I take a line element, instead of taking just a square, the spatial metric looks like a squared times e to the, and we call these beta i's, which depend only time, and then dxi, dxj. And so this is just a spatial metric. And so in each spatial direction, I goes from 1 to 3. This beta evolves at different rates. And that's why and then when one solves the equation, so for the betas, one typically assumes that they sum to 1. And so the square sum to 1, that's why it's Kasner, it doesn't have to be. But if you want to have Kasner, but you can just write down this general metric. And once you vary the action, so to speak, or write down the evolution equations coming from the Einstein equation for these betas, it turns out that you can eliminate them by so they enter, so to speak, simply speaking, the Friedmann constraint, so the 0, part of the Friedmann equation in this simple way, where sigma squared just measures that this is the beta I squared, or sum over the beta I squared. So this is measuring the total anisotropic contribution to the total energy density.
So it seems like a reasonable generalization and so on, but you're talking like it's going to be essential to your.
It will be, yes. That's why I'm adding it in.
Right.
So the simple thing is, but perhaps I can, since the brand, I give a little history. There are two reasons why we added this way. So in the early days, when that was not even a hope for computers, one spent a lot of time, I believe, starting in the 50s, with looking for exact solution of the field equations. And of course, the curved, especially curved Friedmann-Robertson-Walker is one, Minkowski is another, but for cosmologically, it turned out the vacuum Einstein equations also admit exact solutions for this type of Kasner type of anisotropy. Some people know them as Bianchi universes. And so this is we can deal with these type of anisotropies. So this is just the analytics, very simple with pencil and paper because they are exact solutions of the field equations. However, and I will get to this in very quickly actually, it turns out that these are also extremely interesting when one looks at the nonlinear structure. So the vacuum spacetime, and I get it away, and for that we really need numerical relativity to show. If I don't have energy density, or if I have, for example, a canonical scalar with a positive potential or a free field, or if I had some fluid where the equation of state is W has certain quantities greater than a certain number, or smaller than a certain, so absolutely smaller than 3. Now what I get is the vacuum spacetime would naturally, generically, this will be really important for us. Instead of overwhelming you with gradients, converges to a homogeneous anisotropic spacetime. That's one of the main results. So this is.
So this might be tangential to it, but I think if you just take scalar kinetic terms,
Yes, same.
then you get the same.
Exactly. That's perfect. Yeah. So this is the same thing. As a matter of fact, most mathematicians work with when they prove things. So this is one of the big questions. So I hope I can make you sufficiently interested in the second part of the talk. This has been always a really big question in mathematics. What does so contracting, once one assumes a one average contracting universe, and it's in a free field, as Greg mentioned, so a scalar, canonical scalar without a potential. What happens there is that that field converges to Kasner, so sources Kasner type anisotropy. So it exactly behaves like a homogeneous anisotropy in a particular way. Okay, so what I really wanted to write on this equation for a particular reason.
But
yes.
sorry, the
Sure.
asymmetry that the beta introduces,
Yeah,
is that essential? If beta were just one with that,
that would, if it, no, it's not really essential. We just want to give as much freedom as we can. So we could just add there a constant and rescale the scale factor in 3 directions. But we wanted to, so so I just want to come back. I do here everything as far one can get with pencil and paper. And one wants to get to the highest generality one can get with pencil and paper, and that's why the betas were introduced. So it's a really, I think it's a toy, one of the favorite toys of mathematical relativists. They can draw there a lot of nice pictures that give us an understanding what happens. So what I wanted to show is, first of all, we all know it, but when is this happening? Well, what we really do is we add the new energy density component, typically a canonical scalar with some potential energy density. That can be associated with an effective equation of states. And even on a canonical scalar, we know on FRW background assumes the spherical symmetry of the background and behaves the barotropic perfect fluid. So if we have a scalar, then its kinetic energy density 3 times taken over its total energy density is its equation of state. How does one get this formula? One just substitutes the pressure and energy density, which where pressure is the difference between scalar kinetic and potential energy, and the sum, of course, the two is energy density. Substitute back into this simple epsilon formula, and one gets this relation. And we all know, because we learned it at some point in cosmology class, that if epsilon is smaller than 1, right, then all the contributions to the total energy density will be overwhelmed by the contribution to the canonical canonical scalar. Because as you can see here, all contributions to pressureless matter, to radiation, to spatial curvature and isotropy drop in an expanding universe. They all grow in a contracting universe. We'll get to that. They all drop in an expanding universe at different rates. So the one that drops slowest will be the one that overwhelms the energy density. And that will be during inflation, epsilon phi has to be smaller than 1. Many of you know this as a slow roll parameter. One can read it off from here in order for epsilon to be 1. Kinetic has to be much smaller than the potential. So that's what's leading to the circular expansion. And that's everything that I want to say about something that you want to know. Now, we also see that both the dynamical Friedmann equation and the Friedmann constraint are completely blind to whether the universe expands or contracts. So this thing, the only thing what is true in a contracting universe is that H can only shrink. However, in a contracting universe, a shrinking H means its absolute value is growing. So the Hubble radius is shrinking H minus 1 is shrinking very rapidly. So another logical solution would be a contracting universe where you don't have spatial curvature as a problem, but then here is what Planis already anticipated. I introduced this because this will give me exactly the definition but what the naive idea was that we saw, by the way, with numerics is not working exactly like that. Is smoothing when epsilon phi is greater than 3. What happens then, namely? Well, instead of keeping Hubble constant and overwhelming it by the patch growing, we can do the opposite. We can keep the patch constant or nearly very little shrinking. So it is technically constant, doesn't look like that. And what really happens is we shrink very rapidly the Hubble radius around or during the contracting phase. So or at approximately the same. Now, why does this work? Well, how do we know that this works? So one can show that if I add this energy density component, it is not just true that it technically overwhelms the Friedmann equation, the energy density component comes to dominate them, but you also know that this component is a fixed point attractor, both in the slow contraction phase and in the inflation case of the Friedmann-Roberts-Walker system, where the solution is very nice, and there you can read off why we call this slow contraction and why we call this de Sitter-like expansion. Well, simply because we can show, and this is the last thing I do analytically, that this system with a canonical scalar that sources this neat equation of state, either in expanding phase smaller than 1, the contracting phase greater than 3, will lead to, when epsilon is smaller than 1, A growing very fast, H hardly changing. When epsilon is greater than 3, typically much greater than 3, A hardly doing anything, and H is changing. Okay, so far so good. This is all the analytics we're going to do today, exactly around half time. It's a good time to start with moving on to, well, what is the question? And there are two obvious questions. The super obvious question is that I will not discuss too much. Then, sure, if that's not your intent to show, it's reasonable to assume such a patch, which is in my view a valid way of showing, okay, it's reasonable to assume that there will be such a patch, no matter how rare. And then afterwards, we may or may not be able to prove, in certain cases one can prove it, that one gets to the other patch, one starts the mechanism that would be required for smoothing. But once you have a computer, you can do something else. You can ask, let's be completely agnostic of what the metric could be, and ask, what is the largest set of initial configuration metric, an energy density, stress energy configuration that could lead me to either that mechanism or this mechanism? And my focus will be the slow contraction mechanism. But the more important question is really, and that's what I learned to love about numerical relativity, that apart from the obvious question that seem to be obviously answerable with computers, the more interesting part is when you find surprises. And the surprises coming all from the fact that we too often forget, because we got such a lucky break from nature, that these equations, the true Einstein equations, are nonlinear PDEs. And our intuition about how certain initial conditions or any configuration behave when they are governed by this nonlinear coupled PDE system, as opposed, it has nothing to do very often with what the ODE tells us what to do. So this might be a little abstract, but I think by the end, in half an hour, you will appreciate what I want to say. Namely, a more important feature about, a more important question that you can ask is, and that again gets back actually to Glennis' question, did we get this right? Did we get it right that if we start with such a metric, add a canonical scalar with a certain type of potential as sources me, in the ideal case, the right kind of equation of state, does smoothing really occur this way? And what I mean this way is, in a certain set, again, in just a pedestrian way, I tend to call this picture a little patchy. In the sense that smoothing is patchy in both cases, or it's imagined, and really slow contraction, which was over 20 years later introduced then as a theoretical idea than inflation. And that's why also slow contraction is handled very often and treated very often as a dual in this picture to inflation. Nothing really new in the sense of a fundamentally new idea. It just exploits the ideas underlying inflation in a different context. Says start with some patch, which is almost F or W, and what happens is extend the features of this patch over super Hubble scales. But what happens outside of this radius, outside of this rare patch, that's not so relevant. But more important, we don't think that smooth. And all work in inflation mathematical and so far numerical says that in the inflationary case, this seems like a picture. So you overwhelm the volume by this method. So the nonlinear physics behaves actually in the way as it's captured, perhaps for more general initial data than we think, but the essential dynamics is captured by the whole picture. And what I want to show you that in the slow contracting phase is not true. So we got it all wrong, but in a good sense. It turns out that slow contraction doesn't smooth for the reasons, in no way dual as inflation is. And in order to do that, one needs numerical relativity. Now give me 10 minutes perhaps, because what I'd like to tell you is, so simple speaking, what you need to do in order to be able to show what I told you. So in order to be able to run fairly generic initial conditions under the Einstein equations, stress energy source by a canonical scalar, and study what comes out at the end. What is the dynamics? And here I just really want to use the opportunity to tell you a little bit about why numerical relativity is different, both from analytic relativity and also from other types of computation that we are doing. And there are really two, yes.
Sorry, can I just
Sorry,
interrupt?
sure.
So you're going to be telling us about the contracting phase.
Yes.
I mean, in some sense, sort of the most controversial part of the story was the bounce to go from contraction.
That's
to
true.
expansion. Is that going to be part of this, or this will just be?
No, this talk is not solving all problems at once. So, okay, but this is well taken. So, you might ask the question, as Matt says, does it even make sense to look at a scenario without knowing that at the end of this contracting phase, I can connect to a hot expanding phase dominated by radiation and matter? And that's, of course, a very important question. What I'm doing here, and I'm working on that too, and others work on that too. What I'm doing here now is a little bit inverse arguing. Let's just ask, and obviously I'm not the only one who said this, how interesting is this contracting phase? Let's imagine this contracting phase couldn't smooth. Or let's imagine it can smooth very powerfully. But if it can smooth powerfully, it's very important. For one reason, I will never be able to bounce if I don't dynamically generate conditions which are homogeneous isotropic flat on super Hubble scales. There is no hope for that. So if it turns out that it's an interesting case, and in many ways interesting, and I want to say more interesting than we even thought it is, then I think it's worth attacking the hard problem. Can we bounce? Under what conditions can we bounce? And how robust is a bouncing mechanism? Is it formally inconsistent for some reasons, or is it something that I can explode by observations? So this is the philosophy of it, that I consider this both from the relativity, analytic, and computational relativity point of view, but also from the cosmology point of view, a very interesting question, so that it's worth studying on its own, and then it gives me motivation for how to do the bounce. But obviously, this is a very important point, what you just raised.
Also, I thought that one of the problems with the contracting phase was the blue tilted spectrum.
Yeah, that's also a good point. Okay, so I believe, is an easier question to answer, even though non-trivial. So that's again a question, and I just give this excursion because Josh told me good Brown Bag doesn't let me finish what I want to say. So, so the other good point that Massimo was raising is one reason why one likes inflation. That's what I was looking for, is not just that it gives us, or it may or may not give us. There are different point of views, even if it's important that it's smooth. It gives us super Hubble fluctuations by using the same simple scalar that would give us the super Hubble evolution. And what was discovered in the contracting scenario is, by the way, that's also the reason why we expect for simple models of inflation, and of course, this survey is very heavily interested in that they are also there, that gravitational waves would be measurable and produced, hopefully measured by the Simons Observatory. Then this picture would be out, because everything blue shifts here. The gravitational wave perturbations, the scalar field perturbations. So the only thing that you can hope, that's what doesn't have to blue shift is relative fluctuation, different energy densities. So
By
one,
blue shifting, you don't mean that the amplitude is getting big, but just the wavelength
it
is
is
so small.
decaying.
You don't
Yeah,
notice
exactly.
it.
The
Okay.
wavelength is no, but it means that the amplitude is shrinking, decaying.
Okay.
So the wavelength still becomes super Hubble for this mechanism, but the amplitude of the fluctuation decays. Yes, it's the simple reason for it is really from mechanics, that in the Klein-Gordon equation, our damping parameter is the Hubble parameter, and inflation is nearly constant and positive. So it's really damping, and that causes the redshift effect. And in this case, in a simple single field, when the only damping what you can have is the negative, rapidly shrinking, that means it's absolutely rapidly growing anti-friction, that will cause the amplitude shrink. So, and then the only thing and this is something that is my latest paper on numerics, so if there's any interest, I'm more than happy to show it at some point. Of course, relative energy density fluctuations don't have to blue shift. For example, if one takes a nonlinear sigma type interaction, where the one field is kinetically coupled or coupled to the energy density, kinetic energy to the other, then you can mimic the de Sitter expansion on a contracting background. So that problem is, I think, without modifying G, or perhaps in some sense, some of you might not think is an elegant way, but as a matter of principle, solvable problem. The bounce is something that we are working on, but we don't know how robust it is, and you have to make something give. The fluctuations can be solved with Einstein gravity. So that's the difference that, it's more the parsimony that you might ask, oh, do I want to live with 2, 3 scalars or not? Okay, so thanks for both questions. They are really important. I would love to give them both. I mean, they would both deserve actually a separate talk. Good. So let me just say a few words about why numerical relativity is different from how we usually treat GR in a cosmological context. But it has really 3 parts. But the last part is simple. That's what we are used to. So the first part is all codes would have to do these 2 things. But in numerical relativity, you have to do a little bit more work to get that done. So it's setting the initial conditions, it's formulating and evolving the PDE system, and the last one, I won't talk about it because it's really standard. Oh, sorry, it's code validation. So let me just say a few words to both of these, because they are very different from what you would expect. So perhaps I should just say to have the practicality. In order to get to this stage that you can run a code, it typically takes a year. Now, why it takes a year is not because numerical relativists, and both in the cosmology and the black hole context, are bad at coding. The coding part is fairly simple. What takes a year is really these 2 steps for which there is no cookbook. So in some sense, what you have to do is define initial conditions, which are very different from how you define initial conditions in this context. So we all have had our experience when we just want to use a mathematical code or a Python code for evolving these 3 equations and perturbations around them. And we just know what we have to do is from the initial data, the second order equation, for example, if you have a scalar, define the scalar's initial distribution, its velocity distribution, and perhaps the value of the Hubble parameter. And check that that equation is satisfied so that you don't violate the Friedman constraint. Now you have to do it here too, but in a more complicated way. The reason being, and this is what we call constraint satisfaction for the initial condition. And this is really something that why GR codes really have, they are 2 codes. So you write a code, and I explained why, to satisfy the constraint that entails 4 coupled nonlinear elliptic equations typically. Because what are the constraints of GR? Well, we know that these field equations are pretty, they obey Lorentz symmetry, and they evolve all kinds of initial data. However, what we also know, but don't recall that often, they also have so-called bad initial data. And bad initial data are initial data that violate some conservation equations, energy or momentum. So what the constraint equation of GR, like every good theory has a conservation equation, are the projections of the Einstein equations on spatial hypersurface. That's typically your initial spatial hypersurface that you want to evolve in time. And what you do there is you have to look at it if you don't take initial data that satisfies those constraints. The field equations will evolve that. So you can take your code, put it as an initial data, but what will happen is you get bad, you get usually runaway. Either, yes?
I have a question about this initial data.
Yeah.
Is this procedure immune against having a chaotic behavior? So you make some small changes in the initial data and you get erratic behavior?
That's a perfect question. We get there here. That's very good. That has something to do how you formulate the field equations. So there is chaos which is physical. There is actually chaos that people are very interested in, this called mixed master chaos. But we want to differentiate between physical chaos and artificial chaos that would happen only because we have the wrong form of the equation. So we get there in a second. But what's important here is that we really have to find initial data. And this is something that again, the important part about numerical relativity is there is no recipe about this. How do you, certain parts, so we have typically 10 independent metric components and 2 independent scalar for the scalar field components, or if you take the gradients, actually becomes very quickly 5, that you have to specify. The constraint only fixed 4. So a lot of guesswork is needed. How do I find a fairly good set of initial data so that afterwards I specify those that are freely specifiable, can use the constraint to fix the rest. And that's tough because, and this is something that both mathematicians and we in the numerics spend a lot of time on. How do we know how to set the initial data? There are some procedures. You get fairly far, but you will only know how good your guess was once you ran the simulation and saw if the outcome is generically. So that usually takes a long time to do it in the terms of months. And the second part is how do I know that the equations that I'm evolving will behave well if they ought to behave well physically? And that's again something that was this part, something that was an obstruction for nearly 100 years, from Einstein to running a really working numerical relativity simulation, which was done by Franz Pretorius in the early 2000s for two merging black holes. And this has something to do with the gauge freedom of relativity. And the gauge freedom of relativity is a nice feature because it tells you, this is also the principle, one of the principles of how relativity was built, that your physics cannot depend on your choice of the coordinate system. So it's pretty that we have a beautiful symmetry for this theory. Now, what's not pretty is that it gives us too much freedom in writing down the Einstein equation of system of partial differential equations. So this looks beautiful. We got used to the condensed form of the equations, but in order to evolve this system, we have to write it then as a system of 10 plus, given how many equations you need for a stress energy tensor, partial differential equations. And in order to do that, we have to fix the gauge. And we have to fix the gauge in a way that gives us a good set of equations. And a good set of equations is very different from what you think is good. Let's just, again, I won't give here a mathematical relativity introduction, but let me just compare it what we all do and why it cannot be done. So what we all do is, and this is, we really never ask this question when we do pen and paper calculation. And we get amazingly far with it. What formulation, what coordinate system can I use? We usually think of space-time as a foliation of three-dimensional spatial hypersurfaces, and fixing the gauge just means I define the time-like congruence. I define my lapse and the shift that tells me how I thread together the space-like hypersurfaces in time. But this is the so-called ADM formulation, Arnovit-Deser-Misner formulation, which is very useful. It's very parsimonious, and it's great when we want to do perturbation theory, no matter how sophisticated on the background. What turns out is, in the simplest form, when you set the lapse and the shift, as we usually do by algebraic gauge condition, for example, we set the scalar field to be our clock in some sense, as we very often do in inflation, as a so-called unitary gauge, but scalar field doesn't have perturbations, and all the perturbations are encoded into the metric degrees of freedom, which, by the way, at linear order decouple, and we can just label them as different Fourier modes. So it's all simple. But that particular formulation with algebraic gauge condition gives us a so-called bad set of PDEs. That would lead to a situation, and no matter how good my initial data is, the code blows up in very short time, because the structure of the causal structure of the PDE system is such that it creates me artificial blows up. So for the experts, and also simple one can imagine it, what happens is that what we want to prevent is pictorially is that from the energy doesn't flow from long wavelength modes very quickly, so faster than exponential to short wavelength modes. The code, especially in Lorentz invariant theory, would immediately find it, and what we would see is a blow up. And that can, so if it can be physical when it's slower than exponential. If it's faster than exponential, we think it's artificial. And one reason why it can be artificial is if we have a PDE system, we set our gauge conditions that the system is not causal, that the bad gauge conditions causes the PDE to evolve in the wrong direction. This is called some people know it as a Cauchy problem is not solved. Some people call it the equation are opposite. So this is the thing that we have to do often. And okay, so this takes actually more time than that part. So this you can do independently of that guy. But why it takes a long time, that you have to find a formulation which is typical. It takes, okay, do I take, for example, metric-based or a vector-based formulation to represent the space-time components? How do I define the gauge? For example, if I take for our simulations, we use actually a vector-based formulation. Then I have to define the frame gauge. Then I have to define the coordinate gauge so that I represent my vector component. Then I have to plug it into that system. At the end of the day, I have to derive the causal structure of the equations. And only at the end will I know if I did things right or wrong. And more often than not, it's wrong. So once you have a working code, that's great, but it takes, again, several months at least. And the nice thing about it is, that it works. The not so nice thing is, for example, if I do slow contraction, the same gauge cannot be used readily for example, running inflationary calculations. So I cannot go there and immediately repeat what Matt and collaborators have done with my code, because my code actually works for a contracting scenario. And of course we can, and actually we do work on it to check those calculations, but we have to do a lot of work, and this is the part that is difficult. Okay, and now let's just, with the last 10 minutes, oops, show you in a nutshell.
Just a question.
Yes, sure.
The right way of formulating the differential equations is to make them hyperbolic and then also implement the constraints weakly, not enforcing them. But I've seen various implementations, some modifications of ADM or some harmonic gauge. It seems a little bit a cookbook. So is your recipe the same that is used, for instance, for binaries, or it has to be different?
Okay, very good. So obviously, I wanted to avoid saying hyperbolicity, but hyperbolicity is one sign of the PDs that they are well-posed. And for the binaries, so in the well-posedness is we always look for well-posed calculations. So there can be hyperbolic system. If you add the gauge condition, they can be actually elliptic. So that's okay if it's a hyperbolic elliptic system, it should just not change. And the cookbook is in the sense the same, that we can try always with a similar type of formulation. Let's say some of you know it's the Donder gauge or harmonic gauge, where the coordinate of a wave equation, that gets us very far. However, the symmetry of the situation is very often different, and our boundary conditions are different. So in a black hole simulation, you have to watch out for two things. You have a static, often static, or two colliding black holes with asymptotically flat space-time. So they have very different boundary conditions. We get to this in a second. Periodic boundary conditions. And the other thing what's different is the dynamics. So what I want to here, I want to track two scales, for example. So my cookbook is as long as I try their formulations, but then what I assume for the coordinates. I can track here two very differently varying scales. Those are the difference. Those don't tell me. So I cannot just take, let's say, Pretorius' black hole simulation and use it. As a matter of fact, in our case, we use a so-called tetrad or Vierbein formulation, and he loves harmonic. For the bands, what we are trying to do is we actually try now with harmonic, but there is no cookbook for each physical situation. We get pretty far. So we live from what was worked out in the binary black hole, binary neutron star context, but it just gets us as far. And the symmetry of the situation and the dynamics very often tells us, here we have to stop and invent our own. Okay, let me just mention one thing to close, because this is something that is worth learning about. It's actually already, so auto-locality is something that, again, I think one should teach it in basic GR courses because it's so fascinating. Because it's so counterintuitive as to how we would think about gravity if you're in Newtonian gravity or Minkowski gravity. So what you would think is, and what we all think is, what do you think first of contraction? Well, you could say I'm going completely nuts by suggesting that something that contracts will smooth, right? Because our intuition is that contraction leads to mass, little mass, and then at the end, if you cannot balance, to a crunch. But why it leads to a mass is completely wrong in the context of GR. And this is actually, I was a few months ago, Dick Bond pointed out to me, it's already Wismet on Wheeler, that in a contracting universe, gradients actually decay very quickly, as opposed to other terms which are not gradients. So there is never a mass that leads to the type of crunch that you imagine. That was the motivation also to study contracting spacetime. So a conjecture was made by BKL, Galinsky, Paletnikov, and Lifshitz. And this is the conjecture that we have, I think, for the first time, as far as one can get, pushed it to the furthest with numerics, that says in a contracting universe, the terms of your equations, which are spatial derivatives, will be very quickly irrelevant, as opposed to homogeneous terms, which called velocity terms in the first order equation. And the reason why they conjectured this was this. As it turns out, if you run numerics, it's the wrong reason. But why they thought is, okay, if you look at this equation, we see that the spatial curvature, homogeneous spatial curvature term should drop much faster than the anisotropic terms. And therefore, they were interested in what happens if you approach a singularity, classical GR, well, you would get chaos, they conjectured. You would get an anisotropy, this very symmetric anisotropy, so elegant, Kazner-like anisotropy dominated chaos. And one can run actually exactly what Greg suggested, those simulations. I can run it with my code. People actually ran it before me. That was the inspiration to prove numerically, to the extent one can, the BKR conjecture, run it and one sees this chaos develop if one runs it with a free field. But these people never considered was a scalar, and I never told you what scalar I'm using. A scalar with a potential is at the last code, the negative potential energy density. So back in the 70s, 80s, people more thought about fluids. And what people are worried about fluids is when P is greater than rho, because that leads to all kinds of acausal behavior, because in a fluids case, the sound speed goes like P over rho. But in a scalar field case, we know we just have the wave equation. So independent of the potential that for a scalar field determines your effective equation of state, the sound speed is always 1 for a canonical scalar. So we don't have that problem if we learn with scalars. What we also don't have is this type of potential produces a behavior where your background in the homogeneous case will behave like this. And let's say for a mass scale, characteristic mass scale, that's about 0.1 m Planck, one can solve the exact solution. What would come out is that your epsilon phi is 1/2 times m Planck over m, which is squared, which is 50. So it's huge. So it's ultra slow contraction. So that would mean that if this works for generic initial data, then by A changes, so A over A dot is 1/2, H end minus 1 over H initial minus 1 would be approximately 2 to the 50, 1 over 2 to the 50. It's huge. Okay, but what we found, so they didn't discover it, so they concluded that is bad for smoothing, you get mixed master chaos. What we found is the first we confirmed with locality, and this is where I would show you pretty movies. It's very impressive. It's within 1 or 2 e-folds of the shrinking of the Hubble parameter, the gradients are gone. So what's really cool about numerical relativity is you can use it as a device to solve the equations that you couldn't solve by pencil and paper. So what you do is you put the universe into a box. And just for simplicity, of course, the 3 + 1 dimensional box, but for drawing on a blackboard is not so simple. The box in our case has periodic boundary conditions starting with a Hubble size patch, exactly like in the middle. And now you just run the equations for generic initial data, and what you get is, and I'm done in a few minutes, what you really get is that every time you can print anything, whatever you want about the system, the normalized energy densities, the scalar field distribution, the velocity distribution, anything. So it's really like a toy. And it's a great toy because we cannot repeat the universe's evolution. But when you put it on the computer, they actually can evolve under all kinds of conditions. And so what you get is, why do I mention it? Well, because you can also just write down the equation and visualize each term how it evolves in the equation. And this is something we did for the first time in the contracting context. And what we found is you can really evolve the movie of the gradient contributions and evolve the total contribution and see how the gradients really amazingly quickly drop. And this is really GR. So you really see that what you get is an anisotropic curve, but an inhomogeneous space-time, but ultralocal. And ultralocal means that at that point, and why is it cool? Well, because you would think from this picture that the common origin, the common smooth origin, is important for smoothing on super Hubble scales. But the ultralocality tells you that very quickly the gradient vanish. So very quickly each space-time point will develop independently of one another and follow the same homogeneous equation. So even though they start with different initial data, they get to the same state, and that state will be the fixed point of the homogeneous solution due to ultralocality. And that fixed point is if you have this guy, and not a free field, not a fluid, not a positive potential energy density, is exactly one can prove mathematically. We did that too. It's exactly flat FRW. So what's really nice about this is this picture is wrong for 3 reasons for contraction. This state, this Kasner-like state, is never reached. This was a separate project, but what we could show is even though Kasner is a fixed point of the ultralocal state, you can check the basin of attraction of Kasner. You take initial data that is arbitrarily close to Kasner, but what happens is just a little poking on the initial data gives you very far away from Kasner. So what happens really is you never really get to this stage. What you get is an ultra-local but curved state and an isotropic state. And again, I could now show you pretty pictures. And please, when you want to see, just stop by my office, that the curvature plays a really important role. So instead of dropping early, and you have to compensate for an anisotropy, the curvature dynamically destabilizes any fixed point and any solutions that is not a flat FRW. And this was already discovered in the vacuum spacetime, and curvature played a really important role to bump the state from one Kasner point to another. But homogeneous, so curvature that is not depending on space, is really essential for getting you from this ultra-local but curved and an isotropic phase to the flat FRW space. So what happens is it's not that we are not smoothing because we suppress this guy. This guy is never reached. Second, we are not smoothing because we have a common origin. Because as soon as you are ultra-local, and this is within 1 or 2 e-folds, so way before you generate any perturbations of the large patch, every single point is causally disconnected in the sense that they don't interact. So what happens is that you have a massive state, and each point individually finds the flat FRW state. So that's very different from this picture. This is fundamentally nonlinear. So what seems to be the case so far in inflation, to the extent it has been studied, the patchiness that things don't smooth outside of this very big volumetric dominant region is true. In our case, in the case of slow contraction, everything gets smoothed. It has no choice because the common origin doesn't matter. It's ultra-locality that matters. So this is basically, I find, the most interesting result. And I should say, of course, what's interesting is, and that's where we started. The first paper was just checking how generic it is. And it's very generic. So we really got initial data working. We have really good solvers that you can, up to a measure 0 set of initial data, I would say. Of course, we don't introduce a measure, but really you can take arbitrary, almost arbitrary initial data with order of 1 fluctuations nonlinearly, and it evolves to first ultra-local curve, and then flat FRW state on many super Hubble scales. I should also say one more thing before that you asked the question, Vanessa. We have also very robust code. We can run thousands of e-folds. So this has something to do with our trick, how to define Hubble normalized variables using for expert constant mean curvature slicing, that every slice follows the curvature. So before we would reach any, that's why Matt is not anymore here, but that's why we can ignore here the bounds, ignore any crunch without changing Einstein gravity, because our crunch is infinitely far away in time. So that's why it's a robust simulation and we can play with it a lot. Okay, I would stop here, but you already.
That you have to leave because of the kids, or
Yeah, sure.
I have to leave to catch a plane, but I wrote that question.
Oh, then I really appreciate you.
The,
Yeah.
It sounded, that last thing you were saying,
Yeah.
maybe you didn't fully understand it, but it sounded like you might kind of throw out the golden goose by not having any fluctuations at all.
Oh, so that's very good what you are saying. So it's related to the question of Massimo, because if I have only a canonical scalar, so this is not realistic in the sense, I have actual simulation with 2 fields, but I have to throw away the perturbation. So this is really, asking how good is the smoothing mechanism. And I confirm exactly what was the linear conjecture. It has the blue shift. So what we did then, we actually checked, that was one of the last things we have put out a few months ago, this a type of field theory that is minimally coupled to gravity. 2 scalars, the one scalar is canonical, has a negative potential, the other scalar is kinetically coupled, has a kinetic energy that's coupled to this field. So through a nonlinear sigma type coupling, which in our case is just an exponential. And those fluctuations in that field are redshifting because they see a dissociative type background, because exactly for the same reason. It's a very interesting result actually, because yeah, there's a lot of details to it because we got a lot of surprises, but you are right. So if I do it with one field, this is at best good to set initial conditions for a bounce. And if I want to have fluctuations, then I need a second, as far as we know now. Now there might be other solutions, to it, or some people adapt to the bounce inflation. I would not do it personally, but you are right. You're absolutely right. That's the short answer. Sure. Thank you.
Any more questions?
Yeah, actually, in the very early days of the epirotic bouncing scenario, one of the big selling points was that the bounce was an attractor.
Yeah.
And are you confirming that? I mean, the fact that this sigma term is irrelevant and that every single patch follows just the same trajectory, isn't that exactly confirming the what?
Yeah, so I'm not doing any. So 2 points. The idea here is what people earlier called ekpyrotic. Just the only thing is ekpyrotic was always in this brain scenario. We only have classical GR, but they exactly have shown it. That was an important paper by Dan Wesley and Erickson and Steinhardt and Turok that says exactly that's an attractor in the homogeneous limit. So for this scenario, and what we confirm is that is for in fact attractor, but not this. So the flat F4W is turns out to be an attractor of this theory, but not for this reason. So I confirm that what they conjectured is absolutely correct, but not for the reason why they conjectured it. Yes. So no, I'm not. I didn't. This is not my theory, obviously. No, this is. I was unfortunately in school then when they write it. I think it's smart, but so yeah, exactly. I'm working with theories that people write. Right now, it's actually for the bounce. I'm working with theories that Greg and also partially, I believe, you were involved in parts of it developed. So I'm right now interested in how we can exploit what field theorists working in cosmology have done and learn from the nonlinear structure what's possible.
So if I thought, epsilon phi is big, so at small a rho p dominates, I can throw away the rest, including the homogeneity term. And then I have a homogeneous evolution of an attractor.
Yeah.
Would that be correct, at least qualitatively, or not?
Just repeat. So you would say is that
I say, well, the last term is a 1 over a to the 100, right?
Oh, this one, yes, exactly.
So when a is small, I can just ignore all the others, in particular
that's
sigma,
correct. Exactly.
and then I have just a set of the coupled equation.
Yeah. The only thing is that so it turns out that this line element, it's beautiful because it's an exact solution, but it leaves off a lot of possible homogeneous curvature terms, which turn out to be important. So the nice thing, maybe I can add it about numerical GR is, and there are some works with Ulf Danielson and Lehner and Pretorius now that you can check if the background that you believe you can perturb around is an attractor. And sometimes you find that it's different background interesting, and then you can make proofs analytically. So I use numerics as a SOS6 middle tool, and then afterwards we actually the whole, not in the strict sense mathematical, but as far as in physics a proof goes, we actually proved that what you say. Yeah.
Any more questions for Anna?
So I don't know if people can hear me.
Yes.
I do.
So I have a slightly different question. I guess I hadn't realized that there was a way of smoothing things out and creating the initial perturbations through a slow contraction. And I'm just wondering, is there anything that you can say about these sorts of theories that, like, how are they distinguished from inflation observationally? Is there anything that can be said about that at this point, or is it like you have to put in some more ingredients and you don't know what those are yet?
Yeah, it's a perfect question. So I think it's what you can ask is it's easier to answer because there are a lot of flavors of inflation. So you might have your favorite favor and disagree with what I say. So I would just say, is there an observation that would tell you that the slow contracting scenario is not a good idea? That I like to form the question that way because it's easier to answer. And the answer there is gravitational waves from the early universe. If you have, so it's the same question that we asked Sperlinger, and what happens to the amplitudes that only experience the background of the perturbations? And what happens there is that they die because they decay due to this rapidly growing anti-friction, which is the Hubble parameter. And so what happens there is that the gravitational waves would decay. So if the next 5, let's say Simon's observatories, I think will be a really important milestone, because if they find something that would be in line with there was a high energy event in the early universe that had to create, and if the waves are scale invariant or nearly scale invariant, then I think would be in line. There is something in the early universe had to be very highly energetic that generated this mode, which generated the big background friction effect. Something the suits are like. Now, how low you are willing to go?
So just to make sure I got that right.
I'm not yet done. Just let me give me one more.
Oh, go ahead. Yeah.
Okay, but then you can add. And then in a contracting case, you cannot measure them. So if you measure anything with Simon's observatory, or if it will run CMBS4, I'm not entirely sure right now that it will get beyond the Simon's limit. So I think Simon's will be the most important measurement. Then this scenario is out. So that's observational distinction. And it depends really on your favorite model of inflation. If you say you give up at this point, or you say, no, it's completely reasonable to imagine that inflation was so low energy and the plateau was so flat that you don't generate measurable waves. So that I don't want to make that a judgment.
Cool. Thanks.
Sure.
Thank you. It's gonna be here a few years and just sitting on the. in the
So if you
hallway
want to
on the
see
side of the
movies,
blackboard.
then just come back. Exactly.
Yeah,
But again, very good to see you. Yeah, very well. But thanks. Well, yeah, I try to do everything that I do. But then I really appreciate you come. I know you are very busy.
So I'll try to come maybe